Tell me about yourself as a developer. What is checking? Framing, not ego. I'm a junior full stack developer with a strong React and Next.js focus, but I always work end to end. I've built authentication flows, REST APIs, and handle real production issues. What differentiated me is that before development, I work supporting people in Zoom, so I'd understand how payment failures feel from the user side. I code with that awareness. So we have a strong focus with React JS and Next.js, and I always work end to end. I built authentication flows, REST APIs, and handled real production issues. I also work with what differentiated me is that before development, I work with people in Zoom, so I understand how payment failures, retries, of merchant reason codes, etc. So I code with that awareness. Why smart retry? What is checking? Signal versus random applicant. Smart retry sits exactly at the intersection of my experience, payments, failures, and recovery. I've seen decline cards, duplicate attempts, and confuse users in people support. Building a system that handles retry intelligently, safely, and transparently feels like solving a problem I already understand from the inside. So I also have an experience with Bell, reporting payment issues, lost or unauthorized charge or utilization of their card to use for their mobile telecommunication, like internet bill or mobile data. So I've seen those issues, so I understand how important it from the inside. So basically, my experience is more about payments, money, failures, and recovery. Dear Junior, why should we consider you? What is checking honesty plus self-awareness? I'm junior in title, not in responsibility mindset. I've owned full features end-to-end and debug production issues. I made 99%, or I implemented 99% of our capstone or thesis application, which is a teleconsultation for doctors. And I also own things, responsibility, whether it's payment on my previous job, handling transactions, important customer details with care. I also debug our full stack thesis application and all the full stack application I built, whether it's blogging app, full stack ASP with Angular, full stack car application with React, and then I deploy it. I also use I also built two blogging apps connected in the same database with different language. So one is Flutter and one is React. I also don't treat money flow casually. I won't pretend to know everything, but I learn fast and I don't repeat mistakes. React and Next.js, practical, not theoretical. Explain how rendering works in Next.js. What he wants, clarity, not internal trivia. Next.js that you choose where rendering happens. Static rendering for stable content. Server rendering for request-specific data. and client rendering for interactivity. In fintech, I prefer server components or server actions for sensitive logic and client components only for input and display. When would you not use client components? When logic involves secrets, credentials, payment intents, or retry decisions, anything that must be trusted belongs on the server. Client components are for UX, not authority. How do you manage global state in React? I separate concerns. Server data lives in the server components or data fetching layers. Global UI or auth can live in radix or context. I avoid duplicating server truth in client state unless there's a UX reason. What causes unnecessary re-renders in React? Changing object references, inline functions, and overbroad state updates. I fix this with memoization, stable props, and by scoping state as narrowly as possible. Server-side fundamentals. Explain REST like you're designing an API. Resources are identified by URLs. Actions are expressed via HTTP methods. And responses are stateless. I focus on clear semantics, predictable error codes, and consistent data shapes so clients can recover safely. What's the difference between client side retries and server side retries? Critical fintech question. Client retries improve UX but cannot be trusted. Server side retries are authoritative because they enforce idempotency, delays, limits, and logging. So we discuss delays and idempotency and logs, which include transaction ID, correlation ID, retry information, failure reason, transaction ID. So those are for logging. While the delays and limits, those are things that we haven't discussed, meaning the limit on how they can request, because some are actually just trying to hack or trying to do too much requests just to destroy our server. So we also need to have limits. We also need to have delays so that because in idempotency, make sure that the server check first the system before the idempotent key before it returns to the customer. So there's a delay on that. For payments, retries must be server controlled. Explain idempotency. Idempotency means the same request can be safely repeated without changing the outcome. In payments, it prevents double charges when requests are retried due to timeouts or network failures. How would you implement idempotency? Each request has idempotency key stored server side. Before processing, the server checks if that key already exists and returns the original result instead of executing it again. What do you log in a payment system? Transaction IDs, correlation IDs, timestamps, provider responses, or the merchant response codes, retry counts, and failure reasons. Never sensitive data. Logs must allow reconstruction of events. Fintech thinking. What's the most dangerous bug in payments? Silent inconsistency. When systems disagree about what happened, a visible failure is recoverable. An invisible mismatch destroys trust. What scares you about retries? Retries that succeed technically but fail ethically, like charging twice or retrying after a payment decline. Retry logic must respect intent and context. How do you classify failures? Temporary failures like timeouts or network errors are retryable. Permanent failures like insufficient funds or invalid cards are not. Mixing this is dangerous. So not just expiration or insufficient funds, some cards are also invalid. Like it doesn't support by our system. If our system should only support this type of banks, or if it's from another country, so due to legal issue, or if it's a type of card that we don't really accept, such as credit card, etc. So how would you design smart retry at a high level? I'd classify failures, enforce idempotency, apply back-off strategies, cap retries, and log everything. The system should be explainable, not black box. Tell me about a real bug you debug. I debugged with auth issues where users were logged out randomly. The cause was token expiration combined with front-end assumptions. So the state in the front end assumes that that state already expired. So it sent that to the server. Therefore, the server replies back and it log outs the user. So fixing it required coordinating backend validation and front-end state handling. What is a mistake you made? I once trusted front-end validation too much. I learned that clients lie, intentionally or not. Backend validation is non-negotiable. How do you work remotely? I communicate early, document decisions, and make progress visible. In remote teams, silence is risk. Why should we trust you with money-related code? Final closer, this matters because I respect the consequences. I've supported users when payment systems failed, and I carry that responsibility into how I design and write codes. What problems do server-side rendering SSR solve compared to CSR? SSR improves initial load performance and SEO by rendering HTML on the server before sending it to the client. This means users see content faster, especially on slow devices, and search engines can index pages reliably. CSR relies on JavaScript executing in the browser, which delays meaningful content. In Next.js, when would you use SSR versus SSG versus ISR? SSR for highly dynamic data, like user dashboards. SSG for content that rarely change, like marketing pages. ISR when content updates occasionally but doesn't need real-time freshness. The choice is mostly about data freshness versus performance versus cost. So, server-side rendering is a web development technique where the full HTML for a web page is generated on the server for every request. Instead of sending a blank shell and waiting for JavaScript to build the page, client-side rendering, or on the front end, the server fetches necessary data, compiles the HTML on the backend, and sends a fully rendered, ready-to-display page to the browser. Key characteristics: faster initial load. The browser gets content immediately, improving perceived performance. So instead of loading or building it on the front end, since you render it on the back end, you were able to provide that much faster than our client-side rendering. Excellent SEO. Search engine bots receive full rendered HTML, making it easier to crawl and index. That's why you also see that faster in Google because those search engine bots receive the fully rendered instead of ongoing build HTML. Better for dynamic content, good for pages that change frequently, like news, e-commerce, financial technology. So does it request HTML on each link? the short answer is it depends on how the application is built, but traditionally, yes. Here are the details. The classic pure SSR approach, full reloads. In traditional multi-page applications using SSR, every click on a new link triggers a brand new request to the server. The server processes the request, generates a new HTML file for that specific route, and sends it back, causing a full page refresh. For modern SSR, hybrid/frameworks like Next.js or Nuxt, modern web frameworks, Next.js, Nuxt, etc. often blend SSR with client-side routing to make websites feel snappy. So first load, the server sends a full HTML page. Subsequent navigation, the browser often takes over, fetching only the necessary data, like JSON, and updating the DOM with a full page reload. So that's where the advantage of React comes in, because React only updates the necessary update. So it uses a diffing algorithm to change that, the virtual DOM, or it uses a virtual DOM concept to be able to change the DOM. So with kind of like with my app with Firestore, it loads the necessary data as it changes once that fully served HTML has been on the client. So however, in modern setups, if you hard refresh the browser on a new page, it will trigger a new server-side rendering request. So if you hard refresh the browser, like click the arrow circle clockwise on the top left, it will trigger a new request to the server. So summary table feature, new link click, classic SSR, full page reload, new HTML requested. For modern or hybrid SSR, so it used like kind of like with Express or with modern routing, it doesn't necessarily request that on the server. It uses a routing, usually fetches data only, no full reload of that HTML because those are expensive. So it changed per data. So initial load fast, fully formed for classic SSR, fully formed HTML. For modern or hybrid SSR, it's also fast because it's fully form HTML. For backend load in classic SSR, high, all pages generated on request. So there's a high load on the server because on each click, or in each data change, you really request that to the server. For modern, it's still high but mitigated by caching. So in short, well, it's technically designed to render HTML on server. Client-side rendering differs from server-side rendering SSR primarily in where the page is built and how it handles navigation. So does it request HTML for every link? No. In a typical CSR, another thing is that it built it in the HTML bit in the front end, not in the back end. It's being rendered basically in the front end. So in a typical CSR setup like single page application or SPA, the browser does not request a new HTML file when you click a link. Initial load, the server sends a single, nearly empty HTML, like a shell and a large JavaScript bundle. So you can think of it like a skeleton, or I'm a skeleton without full body yet. And all the navigation or necessary JavaScript bundle or dependencies needs by that HTML to compile in the front end. So that's the initial load. That's why it's slow. When you click a link, JavaScript intercepts the click, updates the URL in the address bar, and dynamically swaps out the content on the current page. It usually only fetches raw data like JSON from the server to fill in the new view. rather than a full HTML document. So it's kind of, this is the feature of the hybrid server side, where when you click a link, the JavaScript also interferes with its route behavior in the address bar, and it dynamically swap out the content on the current page. Key difference at glance feature, where HTML is built, server-side rendering on the server for every request, client-side rendering in the browser via JavaScript. So the difference is really how it is built or compiled. First load, fast, the browser gets ready to show HTML immediately. For server side, for client side, slow, the browser must download and run JS before showing content. Link clicks, usually for server side, usually triggers a full page refresh, new HTML. For client side, snappy transitions, no page refresh. Refresh content updates instantly because JavaScript intercepts it. Server load, for SSR, it's higher. The server works hard for every visitor. For client side, lower, the server just hosts static files and data APIs. It's kind of like it doesn't it has a data APIs, like the database APIs to connect to the database, and it's just like a static host files. It doesn't really build the server doesn't really works hard for each visitor. It just serves those static or skeleton. SEO for server side, excellent. Search bots easy to read the full HTML. For client side, it's difficult. Bots may struggle to see content hidden in JS. So for next question, so again, SSR improves initial load performance and SEO by rendering HTML on the server before sending it to the client. This means users see content faster, especially on slow devices, and search engine can index page reliably. CSR relies on JavaScript executing in browser, which delays meaningful content. So in Next.js, SSG and ISR are strategies for creating static HTML files before a user even asks for them, ensuring the fastest possible load times. Static site generation, SSG creates every page of your website during the build process. So when you run next build, how it works, Next.js fetches data once, generates the HTML files, and save them as static assets. So it doesn't really, change as the data change, because it was marked in the server or Next.js as a static. It only generates that on initial, the data in the HTML on initial load, but after that, it won't change. The server serves the exact same pre-built file to every visitor. It is lightning fast because the server does zero work at request time. So it is not rendered or built in the server, so it's slow. It's not like fast like a server-side rendering. Downside, if your data changes, like a typo in a blog post, the site stays still until you manually rebuild and redeploy the entire project. So if your data change, or you need to change some typo with your user interface, you need to rebuild and redeploy that, or the user need to request that again. So it's best for blogs, documentation, and marketing pages that really change. Incremental static regeneration. ISR is an upgrade to SSG that allow you to update static pages after you have developed your site without a full rebuild. So it's an upgrade to SSG. So how it works, you set a revalidate timer, like 60 seconds for that. For that minute, everyone sees that static cache version. The magic moment when the first visitor arrives after the timer expires, they still see the old state page immediately, so they don't have to wait. However, Next.js triggers a regeneration in the background. Result, once the background build finishes, the cache is updated. The next visitor gets the fresh version. Best for large e-commerce site, new portals, or content-heavy sites where data changes periodically, but you still want static speed. So feature, when it's built, for SSG, only at build time. For ISR, build time plus background refresh, rebuild the ISR. So if you want fast and also keep those changes, you would want ISR. Update method, SSG, requires a full site redeploy. ISR update automatically per page. Data freshness can become very stale. ISR stale fresh based on your timer. Speed instant. ISR instant serve cache version. What happens internally when a user hits an XGR SSR page? The request hits the Next.js server. Data fetching functions run on the server. React renders the HTML and the fully rendered page is sent to the browser. After that, hydration happens, so React becomes interactive on the client. What is hydration and why can it fail? Hydration is when, So with Next.js server-side rendering, you're rendering on the backend or you're building that on the backend. Data fetching functions, the data that provides those that fetch data to the function of your application logic or runs on the server, not on the client. React renders the HTML. So once Next.js send us pre-built app, the React on the front end will now control the app application or the HTML and then sent to the browser. So after that, hydration happens too. So React becomes interactive on the client. What is hydration and why can it fail? Hydration is when React attaches event listeners to server rendered HTML. It can fail if the HTML generated on the server doesn't match what the client expects. So basically, you're having like a UI bug because like an event listener listening on the server and that server sent that HTML, but that's not what expected by the client. So you get a bug, usually due to non-deterministic values or a value that occurs non-deterministically or it's not deterministic, because if it's deterministic you get the same value each time, but if you have date non-deterministic like date.now, random numbers or browser only APIs could hijack that and provide unexpected value. So why is doing heavy logic in SQL sometimes better than in front end? Because SQL operates closer to the data, reduces network round trips, ensures consistency, and enforces business rules centrally. So since if you have all the most or a lot of your logic in SQL, it operates close to the data. Therefore, you don't need like an application code to kind of like maintain those security or logic that you want to keep on your application. So you have like less network round trips. You also have more consistent data. You also have more secure data, and you also have like fast performance because it's close to the data. Therefore, your logic could perform that. And also you have less like overhead as a developer. Instead of like thinking of those hard, non-deterministic issues or problem, you fix that at the back end. Therefore, you get less complex code in the front end. Uh, that's also how sometimes like pulling the complexity downwards instead of upwards, because like if you build complexity downwards, we were able to abstract it on the user, on the client. So the client will just need to tap that interface for them to be able to use it, depending on what we allow them to do. So basically, it actually leads to more simpler and maintainable code. So it enforces business rules centrally, front-end heavy logic, risk duplication, security issues, and mismatch results across clients. Explain plus one query problem. The n plus one problems happen when one query fetches a list, and then each item triggers another query. So this causes performance issues. The fix is batching, joins, or eager loading to reduce query count. So basically, you have this like domino effect. So a query will trigger the item in that query, uh, that the return list and items on that query triggers another query. So you get this performance issue. So the fix is joining or batching that, or combining them in one fetch, or joins in the database. So you join that that related data, or eager loading to reduce query count, or provide that query or data ahead of time to the customer. So eager loading is a data retrieval strategy where you fetch all necessary or related data immediately during the initial request rather than waiting until it is specifically needed. It is like sort of like caching ahead of time. While not strictly caching in the sense of storing data in separate cache like Redis, it shares the same goal of proactivity. Caching typically stores data for future requests across many users. Eager loading preloads data into memory for the current request, so it's related to use instantly. So it's ready to use instantly without another trip to the database. So if you know that the customer like are requesting this type of data, you would and all of this related data is frequently requested, you will eager load this data as well so that you avoid that request. How does Supabase real-time actually work under the hood? Supabase listens to PostgreSQL's logical replication stream. Database changes are captured, published as events. So PostgreSQL, a logical replication stream, or kind of like, uh, this Supabase, like kind of like the listener of that PostgreSQL replica. And when that PostgreSQL database changes are captured, it is published as events and pushed to clients via WebSockets. So it pushed to the Supabase via WebSocket. Clients subscribe to channels and receives update without polling. So it doesn't use poll. It subscribe and receive updates via WebSocket. Why is WebSocket preferred over polling for real-time systems? WebSocket maintains a persistent connection, allowing the server to push updates instantly and persistent. I mean, and that connection are persistent. Polling wastes bandwidth, increases latency, and doesn't scale well under load. So a polling, on the other hand, wastes bandwidth, increases latency, and doesn't scale well under load because you need to like constantly request instead of persisting that request on one go or for like a period of time. What are the trade-offs of real-time system in fintech? Real-time improves UX and observability, but adds complexity. Connection management, security, consistency guarantees, and failure handling. In payments, correctness matters more than speed. So real-time must be carefully scoped. So since payments, more than any other industry, requires us to provide a real time because any if you like don't follow real time, you could provide a wrong balance to the customer. So correctness more matter more than speed. So that real time must be properly scoped or implemented by the application. How would you design a retry system for failed payments? I'd base retries on recent codes, time windows, and customer behavior patterns. So with customer behavior patterns, that's uh, like the key or the what we do in PayPal and Bell as well. A lot of times when we're trying to decide their payment or how we are gonna deal with them, it's really always depend on context or depend on each situation. But a lot of those interaction really rely on their previous transactions with us. So behavior patterns and the reason codes for that payments, whether it's temporary or permanent failures, whether it's merchant, time windows, how long. Time is always important. That's why we have timestamp. We have expiration, etc. Use exponential backoff, avoid retry storms, and ensure idempotency so retries don't double charge users. What is idempotency and why is it critical in payment? Idempotency ensures that repeating the same request produces the same result. In payments, it prevents duplicate charges when retries or network failures occurs. How do you prevent race condition in backend systems? Through database transactions, rule-level locking, optimistic concurrency control, and designing operations to be idempotent. Sometimes queues are used to serialize critical operations. So database basically provide that inherently nowadays. You row level lock, so you make sure that it's locked in row level, and optimistic concurrency control, meaning there's no like in between. It's either completed or not completed, and you ask the payment or the client to request, and you design the operations to be idempotent to avoid that retry. So you kind of like have this mini checks along the way, not just on the server, not just on the front end, not just but especially on the database. So sometimes queues are used as well to serialize critical operations. So sometimes you have this most important operations such as like sending this large transaction. So you would want that to put some on kind of like a priority queue to be able to handle that really well, or focus or provide energy on those transactions, or kind of like make that put a lot of resources, or think about those the concurrency, the ACID on those transactions more carefully than other transactions. So what is eventual consistency and when is it acceptable? Eventual consistency means data will converge over time. It's acceptable for analytics or notification, but not for core payment authorization or strong consistency. is required. So eventual consistency, meaning that the data will be converged or will converge over time, will be the original data over time. It's for analytics or notification. It's not really for payment authorization or anything that change customers' money. So only for like useful analytics and notification to the customer. How would you structure an Node.js microservice architecture? Each service owns its data, communicate via HTTP or events, and is independently deployable. So I would create like the API for or each um, service as an independently deployable. Basically, I would make sure that it follows REST rules. It can be tapped by I don't know it can be request or it can be communicated via HTTP or events or event listener from the front end, and it could be independently deployable, not dependent to other components. So shared logic is minimized. Observability, logging, tracing, metrics is built from day one. Why do startups often start monolithic and later move to microservices? Monoliths are simple to build and reason about early on. Microservice introduce operational complexity and only pay off when scaling teams and systems independently becomes necessary. How does TypeScript help in large systems compared to JavaScript? TypeScript adds static guarantees, improves refactoring safety, document intent, and reduce runtime bugs. So static, basically you're trying to define it ahead of time to avoid those runtime error. So you kind of like define it or being conscious of it before you even build it. So it improves the documentation. It improves the bug findability, especially important when multiple developers touch the same code base. Static typing versus dynamic typing, which is better for learning CS fundamentals. Static typing helps beginners understand data structures, constraints, and system boundaries more clearly. Dynamic typing offers faster iteration. Ideally, learning both gives the strongest foundation. What happens when a Node.js server receives 10,000 concurrent requests? Node handles concurrency via the event loop and asynchronous I/O. CPU-bound tasks block the loop, so those should be offloaded to workers or serve separate services. So a CPU-bound task, it will be offloaded to workers or separate services. So a node basically handles the concurrency via event loop and asynchronous I/O. So how do you secure server-side APIs in a front-end heavy app? Authentication via tokens, authorization on the server, rate limiting, input validation, and never trusting client-side logic. Front end is just a UI, security lives on the back end. What makes a senior level answer different from a junior one? A senior thinks in trade-offs, failure modes, scalability, and business impact, not just code correctness. They design for things going wrong, not just things working.